Hi, everybody. I'd like to welcome you to SDC 2022. My name is Danny Moore. I'm a contributing member of the CXL consortium in the marketing working group. And I'm also currently driving product management in the CXL space for Rambus. Today, I'm going to walk everybody through some of the things that we've been working on in the CXL consortium, some of the high-level benefits and market needs that we're seeing in the industry, and really why the industry is building all of this momentum around CXL for the next generation data centers. There will be a Q&A session after the presentation, so please feel free to post any questions that you have, and I can try to address them at the end of this talk. So the first thing at a really high level are, what do we see as the main drivers in the industry? There's massive expansion of cloud computing that we obviously see all around us, huge growth in AI and analytics, which again is driving massive expansion of compute resources, and then correspondingly the various different database requirements that go along with that. The data growth itself, but then also, how the data is moved, accessed, and then stored both to and between those very same resources. We see much of the network and edge is also moving to the cloud and pushing those same requirements. Each of these drivers is demanding faster and more powerful processing elements via arrays of, CPUs, FPGAs, custom ASICs, GPUs, and correspondingly with this increase in these heterogeneous compute resources, we need to start balancing those system requirements with access to more and more memory with higher bandwidth, larger capacities, while still maintaining low latency performance targets. So at CXL, we've been working to ensure that we deliver the right mix of feature sets and architectures to ensure that we're meeting those compute needs for the next generation data centers. CXL is an open industry standard that's really bringing three main pieces to that evolving landscape. Number one, it's bringing a coherent interface that's really mixing three new protocols. So .io, which is really a packetized version of PCIe, which is used primarily for device initialization and enumeration. And then both the .cache and .mem protocols bringing both a cache coherent interconnect as well as memory expansion, all with the load store semantics that hosts and host software are used to seeing on their infrastructure. Two, a low latency architecture with .cache and .mem protocols targeted at or near CPU cache coherent latency levels. And then finally, what we call asymmetric complexity. As we standardize the CXL interface, designs are able to be used on different processors, different accelerators, and can even be used and reused on different generations of devices. So for example, media types are no longer going to be tied directly to the processing element itself. As long as you have a CXL interface, you're going to be able to attach to compute resources across a wide array of vendors, like I mentioned previously, custom ASICs, CPUs, GPUs, etc. So here we show a graphical representation of the 2.0 usage models. There's really three separate types of devices defined in the CXL specification. We've named them type 1, type 2, and type 3 devices. All three device types support CXL.io. That's a mandatory piece, which is really needed for enumerating the system and device initialization. But each device type is differentiated in the mix of .cache and .mem protocol support. So starting on the left, we have the type 1 device. the .cache protocol is added to the .io protocol support to form the type 1 device. And we can think of these type 1 devices as accelerators or smart NICs, or really any device that wants to maintain a cache coherent interface with the processor memory itself. Then moving to the right, the type 2 device, we add the .mem protocol to the type 1 device. And here we see, dense clusters of compute resources, again, FPGAs, GPUs, where the devices can now retain, cache coherent copies of host memory. But with the addition of the .mem protocol, now the host is able to access directly the device memory with the very same load store semantics as it would access its direct attached native DDR interface. And then moving to the last device type 3 devices, the .cache protocol has been removed. So we have .io and .memory support only to really build a device class that is focused purely on the memory expansion. This really creates a new serialized data path to enable both memory bandwidth and capacity expansion with those same host-based load store semantics that we're all familiar with. Now, expanding on those usage models, CXL 2.0 also enables a switching hierarchy so that we can really see those same load store semantics being expanded to more and more devices. The switching concept in CXL really provides the fan-out style device expansion that we would historically see with PCIe-based switching. So now hosts are no longer bound by the number of interfaces on their own devices, but rather have a method to fan out to attach many, many more in much larger hierarchies. With the advent of switching in CXL, we're enabling larger and larger clusters of resources that will still benefit from those familiar semantics, unlike the block level transaction types that we would historically see on PCIe-based hierarchies, but while all maintaining those similar low latency and high bandwidth design requirements that we see in CXL. So we show a couple examples here. On the left, both of these are single host examples. On the left, we have a single host and a single switch showing expansion to 4 devices. And then on the right, a similar example, but showing a multi-switch implementation to kind of show additional switch expansion. And then what follows naturally from switching are a couple of useful use cases around what we're calling pooling that's enabled in 2.0. Pooling-based solutions for single logical devices for both memory and accelerator type devices, or really any other single resource. And then memory-based pooling solutions for memory-only based pooling solutions for multiple logical devices, MLDs, which have been architected in CXL 2.0 for memory only. In the example on the left, we see the single logical devices attached to different hosts in a composable manner. Host 1 is connected to device 2 and device 3, device 1 connected to device 2, device 4 connected to device 3, host 3. But then on the example on the right, we take the composability a level further to really enhance the use case by the addition of MLD type 3 devices. In the diagram, we have a logical abstraction of the physical resources that can be assigned and reassigned to the hosts as we see fit. On the right, looking at device 1, we can see that all of its resources have been fully assigned to host 1, with partial resources in MLD device 2 and MLD device 3 also being bound to host 1's virtual hierarchy. Whereas some logical device resources in device 2 and 3 and 4 have been bound to host 3, and logical devices in 3 and 4 being bound to host 2. So, the combination of multiple logical devices, MLDs, and pooling really build a fully composable path to memory expansion, where resources can be wholly or partially shared across host interfaces in an as-need manner. Some of the additional features that have been added post CXL 2.0 in the form of ECNs include memory interleaving enhancements. Memory interleaving is something available to directly attach native DDR. It's been available for quite some time, which really allows hosts to improve performance by spreading the bandwidth requirements across the memory interfaces in an interleave manner. In 2.0, we originally defined an ability to interleave memory devices, but we supported only 2-way, 4-way, and 8-way interleaves. The thought originally in the consortium for 2.0 was that we wouldn't start off defining too many interleaving options, rather we'd focus on a smaller subset. But as the ecosystem continues to grow, we really do see tons of interest in the Type 3 memory expansion usage model. So we felt there was a need for us to beef up the interleaving capabilities to match the options that are currently available with native DDR. In particular, system designers are trying to match memory capacity and bandwidth with various compute capabilities or system requirements. Maybe it's number of cores or restrictions to the number of I/O channels. Cost is obviously a factor. And, jumping between a 4-way to an 8-way interleave had a large impact. So we really see the new 6-way interleave option as a sweet spot that can enable kind of a large set of different system implementations. Now, obviously, there's some added complexity with the addition of some 3-way math, which is needed in both the host and the devices to enable the 3, 6, 12, and 16-way options. On the right, we see a 6-way interleave implementation. Here we're taking 6 terabytes of memory that's shared across 6 Type 3 memory devices. So each device showing 1 terabyte of memory capacity. And this interleave is actually accomplished in 2 stages. The first stage, the host-specific logic will use the mod 3 math to select one of the 3 host bridges at a 1 kilobyte granularity. But then each host bridge will use a simpler 2-way math to select the root port that the transaction is routed to at a 512-byte granularity. This way, the device will see a 6-way interleave in a 512-byte granularity, really allowing the bandwidth to be shared across all 6 interfaces, all 6 CXL interfaces. And then, moving on to a slightly more complicated example, we show a 12-way interleave here, which involves an additional stage in the hierarchy. In this case, we're using 12 devices, each with 512 gigabytes of capacity for a total of 6 terabytes of memory expansion, like the example provided previously. And like the previous example, we still have the host logic performing the same 3-way math, the same interleave at a 1 kilobyte granularity. And the host bridges are performing the same action in a 2-way 512-byte granularity. But now we see that each root port is actually connected to a switch below it, showing a total of 6 switches here in this example. And then the switch itself is providing a 2-way interleave at a 256-byte granularity. So the device converts the host physical address to a device physical address, in this example with a divide by 12 operation. And so each device receives 1 out of every 12 256-byte chunk. So once again, the total bandwidth now in the previous example was shared across 6 CXL interfaces is now going to be interleaved across 12 independent CXL interfaces. So now we, with the addition of these interleave options, we really start to see CXL attached memory is beginning to support more and more of the same feature set that we're used to seeing on directly attached DDR interfaces. Some more benefits of CXL 2.0 was the some features surrounding persistent memory. As we see CXL continue to disaggregate the memory interface from the host, we can build solutions that can attach an endless array of different classes of memory. So we can now take classes of memory and use them to fill a gap between, the higher performance interfaces like CXL attached DRAM or CPU direct attached memory, and much higher latency interfaces such as NAND-based flash storage, for example. These classes of memory can include higher latency, but more cost-effective capacity, and potentially implement some persistent memory solutions as an option as well. Once again, all while maintaining that same familiar load store semantics that the hosts are used to using, kind of providing some additional memory expansion. A feature called Global Persistent Flush was added, or GPF in 2.0. So non-graceful events like sudden power loss or other events can now trigger a flush from non-persistent media types to persistent media types. So this way we can really ensure that any in-flight or in-use data is captured and saved to our persistent media. CXL 2.0 really brings security to the forefront. Encryption and security capabilities were added, which can be optionally supported. Really modeled after PCIe's IDE implementation. The consortium added some enhancements for .mem and .cache protocols. We're able to protect communications across the physical interface itself. And this protection will include both point-to-point communication as well as full data paths, which may include switching elements. And this support in 2.0 for IDE was really bolstered by the IDE Establishment ECN post CXL 2.0 spec release. And really we see IDE accomplishing two major things. One, it ensures any modifications to the traffic between two link partners can be instantly detected. And two, it protects in-flight communication against snoop or theft of user data. The link partners need a set of symmetric keys, so obviously they can encrypt and decrypt communications. And this is the ECN that really describes in detail how hosts or other agents like BMCs can communicate with IDE-capable components via a CXL-defined set of messages we call CXL IDE KM, or CXL IDE key management. These messages will configure and provision the keys for the link partners and finally ask the components to initialize or tear down the IDE sessions themselves. You can see on the right quite an impressive looking software stack, but everything here is really leveraging existing industry standards and ecosystems with just some of the additional CXL defined messages sitting on top to fully enable IDE and CXL for both the .mem and .cache. And finally, we have a quick little sneak peek or a little teaser for the audience into the upcoming CXL 3.0 specification. Those industry trends that we really saw driving the CXL 2.0 specification are still driving for further feature enhancement into CXL 3.0. We want the same interconnect that provides system level flows to those same components, but with some additional advancements, in switching, peer-to-peer capabilities, and of course, addressing the needs to share resources now, not within host domains, but outside of host domains in, kind of a fine-grained methodology. So, at an electrical level, we do double the bandwidth to 64 gigatransfers per second. We're sitting on PCIe Gen 6 electricals, and we've specified some new memory usage models that will enhance the memory pooling use case, in addition to the fabric capabilities that I really mentioned above, and multi-host and multi-level switching, and then obviously enhancements to the fabric management itself to really help drive the next generation of the composable rack. And of course, we maintain backward compatibility to the previous specification releases, 2.0, 1.1, and the 1.0 release. So please stay tuned. The specification is due to be released later this year. And you can get more information for that at www.computeexpresslink.org. Thank you very much for your attendance. Please feel free to stick any questions in the portal, and I'll stick around for a few minutes and try to answer them for you guys. And if you could, please take a moment to rate this session. Your guys' feedback is important. All right, thank you very much. I'll see you in the Q&A.